Hello, everybody. I'm Jason from EZKL, which is a framework for machine learning with ZK. Before I start, I want to kind of take a moment to think about, with you, about, what are we doing this for? So, like, what's the point, right? So imagine that a friendly grandma asks you, what is the problem that you're solving, right? People ask us a lot about our business model and kind of legitimacy of what we're doing. I think we're solving important problems. I'm not sure if the friendly grandma does. And I'd say that the problem that we're solving is basically that people lie on the internet, right? So that is fine and entertaining, but it's also a problem when it comes to financial transactions. And in some sense, the only thing that blockchain is good for is to create a shared collective truth that we can all reference, right? The historical solution has been trusted third parties, right? So if you go back to the 1997 Szabo paper, he was already pointing this out, right? So the thing we start with is we have a mutually trusted third party. We want to do a financial transaction, we trust the bank, right? We want to do an identity transaction, we trust, Mark Zuckerberg. And we've been able to, he envisioned replacing that with a mutually trusted virtual computer. This was almost 30 years ago. We've been building that computer ever since. This is the main working version of that computer, right? This is a trusted virtual thing that we can all share, and that prevents us from lying on the internet at the cost of consensus. But, it is still a bit slow, and it doesn't do everything we want it to do. And so, the role of ZK, ZKML, which I'm telling you, but ZK in general, is just to expand the space of things that the EVM can do, from this relatively restricted thing to broader types of computation, much more complex functions. Of course, I'm telling you things that you can do with EZKL, which is a particular framework for writing in ZK, and you don't really care about what the EVM can do, right? You care about what you can do, because if you can't get it to work, then it's infinitely slow. So what is EZKL? It is, in our opinion, the easiest, fastest development loop in ZK. Having a tight development loop is critical to advancing the space and to exploring all of the ways we can expand that little bit of consensus, the little crystal of consensus that we've built with Ethereum. It's a compiler that turns ML and AI models into zero-knowledge proofs. It compiles from Python with 15 million developers, so we're trying to onboard a lot more people into kind of Ethereum and its orbit. And it verifies on-chain with EVM or in other low-resource environments. We have JavaScript SDK, and we have, like many other folks here, a cloud service that lets you delegate your proofs to us if you prefer. And one of the cool things we can do is you can do everything in a IPython notebook. So you can open it up on Google Colab, you can define your circuit, you can compile your circuit, you can deploy it to the back end, and you can do something else cool, which we'll see in a minute. So yeah, you're specifying your logic, your AI logic or your app logic in general in Python. We're using Rust and kind of our variant of Halo 2. Maybe we should call it Halo 5 if we were better at marketing, to turn it into a zero-knowledge proof. And then you can deploy Solidity verifiers. You can use TypeScript and JavaScript on the front end and back end. And if you like, we can help you with proving and serving, but it's all open source. So if you don't like, you're very welcome to run it yourself. And please do. And now we have GPU acceleration, thanks to Ingonyama. OK, but why Python? This is the percent of developers that know Python. This is the percent that know Solidity. This is about 15 million. This is not that large. And then if you go to sort of ZK circuit languages, you'd see the same relationship again, right? So Python is a way for us to access a much broader universe of developers and get a lot of work done quickly. So we make it possible, as I said, to do everything from a Google Colab notebook. You can automate the calibration, the fiddly parts of the ZK to choose your circuit parameters. You can set up the circuit from Python. You can prove, create EVM verifiers, deploy the EVM verifiers, and check that they work. The model definition language is nothing special. It's just you can use PyTorch. You can use TensorFlow. This is PyTorch. You just write normal PyTorch, and then you compile it. You can use sklearn, so you can do traditional data science stuff with it. This is a gradient-boosted tree. And increasingly, you can use more general computations. So this is an example of proving and verifying on the mobile browser with our JavaScript SDK. So these are local proofs and verifies. And one of the fun things you can do is if you don't mind paying a 10x cost, you can verify with the EVM contract in the browser, which is also kind of fun and kind of makes you wonder why not use EVM everywhere. I hope in the future all web apps will be written in Solidity, but we're a ways from there. And if you've been over to the Devconnect venue, you probably used the ZooPass. We also let you program ZooPass itself using EZKL if you want to deploy a new logic to ZooPass. Whether it's just a simple set membership proof, which we can support, or more complex things that use machine learning models, you can do that as well. And there's a talk by our team member Casey on Friday about that at Prague Crypto. People often ask us which models work. So lots of things work. It's a bug if it doesn't work. If you can express it in PyTorch or TensorFlow and it doesn't work, please tell us. So neural nets, vision, decision trees, as I mentioned, random forests, and those kind of things, which are very widely deployed in industry and which win Kaggle competitions. We can do transformers and small, large language models, which is a bit of an oxymoron. Those are getting bigger and bigger. Nano GPT, when we first launched, it took about half an hour, and now it should take less than 2 minutes. It might be 1 minute at the latest. Self-attention, all sorts of things like that. Classic statistics and data science, descriptive statistics, regression, all that kind of thing. The world runs on regression. And we're doing increasingly general purpose logic like set membership, proof of solvency, whatever you like. We like the AI model, ML model, so we're still sort of thinking through with you kind of how best to extend the logic other than just handing you a virtual machine, which we think is too general to be helpful right now. How fast is it? Okay, so everyone asks how fast and how big. So there is actually no limit on how big anymore because we figured out a way to split proofs up into chunks. So that's not something I can meaningfully answer. But I would say that really what matters is the rate of improvement, right? So GPUs themselves that run neural network models, they double every 2.5 to 3 years in terms of performance or flops per dollar. So as long as we're faster than that, eventually we'll catch the state of the art. And right now we're going much faster. So we're about 18,000 times faster than we were a year ago, and this is actually a little bit out of date because last week we shipped some things that dropped proof time by about 30 or 40%, just algorithmic changes. And that's before GPU acceleration, which we're here to talk about. And in some ways, more importantly, is not how fast is the computer, but how fast is it for you, right? So how long does it take you to build a new app with this? And our goal for that is minutes. Right now it's still realistically hours, kind of hackathon scale, but it used to be a lot longer. So we'd like that to be as push button as possible. And so, kind of our philosophy in summary is, as I think many folks have said, that ZK app development today feels like a lot of math, a lot of custom languages, clever circuit writing. I'm a former mathematics professor, so I love that. If you love that too, please write awesome circuits. If you love it slightly less, this is fun too. It's just open source, so you can actually, even if you don't like the compilation we've created, you can dig in and change it however you like. And there's limited targets for proving and verifying. And managing cryptographic artifacts in production tends to explode in your face when you're not careful. So our goal is to make it so you could, in theory, do everything on a mobile phone. Create the model, deploy it from the notebook. We can manage the proof version artifacts for you if you like. And you can prove and verify on mobile or check that it was verified on mobile. Okay, so now finally I just want to talk a little bit about GPU acceleration and our kind of experience with it. I think for everybody looking at this field, right, GPU acceleration is really exciting. It's got sort of great potential for improving the performance of proofs. But CUDA, right? So it's really a pain to integrate. It's a pain to install, and it's pretty annoying. So we're very thankful to the team from Ingonyama for helping us build this out for EZKL. GPU proving on the good side is super fast, but on the bad side, oftentimes it's closed source, right? So lots of GPU proving is happening behind the scenes. There's a sequencer. It computes proofs. You can tell the proofs are correct, but you don't get access to the GPU bindings. So the GPU bindings are restrictively licensed, or they're hidden behind a cloud in order to protect a business model or revenue. So we kind of say, screw that. Ingonyama and EZKL. EZKL is open source, EZKL is open source, and you can do now GPU accelerated proofs, EZKL proofs on your device today, on your laptop, or even in your browser. And what you're going to need to do is, normally you would do pip install EZKL, and now you're going to have to do pip install EZKL-GPU and have a GPU, and everything should work. And I think, yeah, so if you want to check that out, this is a link to a Google Colab notebook in which GPU proving is enabled. So when you go to the GPU, when you go to the runtime of the Google Colab notebook, you can select runtime, pick a GPU, like a V100, I think are in the free tier, and you can run through the notebook, and the proof will be computed by the GPU. That's all. Thank you. Yeah, any questions? Yeah. All the way in the back there. Oh, I see. Oh, well, that too.
So you said the GPU acceleration is already available right now? It's already a feature, not testing?
Yeah, it's a feature. If you follow this link, you can run GPU in your browser on a Google Colab notebook. Right
Okay,
now.
we'll try. Actually, we just did a hackathon project with your product, but we just ran it on the CPU. It's, it takes time, so we really want to try the GPU acceleration.
Cool. I mean, it varies a lot by circuit right now.
Okay.
And I think hopefully it will continue to improve. You're going to see probably about 50% faster, or like 2x, speed improvement. Hopefully that should start to become 10x, depending on the circuit. But we need to tune it more. And the way we tune is people tell us, I want to run this circuit. It wasn't as fast as I liked, and so we'll figure out, what went wrong. Yeah, so please tell us. Yeah, if it's not good. Yeah.
Thank you.
Yeah, I have a question. Actually, two questions.
Yeah.
So the first one is, I wonder how you guys constrain the Python scripts in the sense that, like, I wonder if you guys have come up with a way to somehow statically parse the Python scripts and then compile down to Halo2 script. Yeah.
That's a good question. So to be more precise, what we're actually compiling is Onyx. So, which is a way to record a neural network or other computational graph. What an Onyx is basically you take the abstract syntax tree of the computation and you dump it into a protobuf in sort of the most straightforward way you can imagine, but it is a standard. So PyTorch, TensorFlow output that. When you do a scikit-learn can be transformed into that. Other things can be transformed into that. So that's kind of our intermediate representation, which is a static computational graph. And the reason we like it is that because of that 15 million Python developers, it's the most widely deployed circuit language. Right? More people know how to create something that outputs as Onyx than any other type of circuit representation. And so it's a great intermediate representation to work with if you want to reach a broad audience.
Thanks. Second question. In which part do you try to use CUDA? Is it on the arithmetization part or polynomial commitment part? Where do you use
mainly
the
on
GPU?
the commitments, the MSM, and TT stuff, yeah.
I see, yeah.
All right, thank you.